Okay, section 4.2, the mean value theorem. We're just going to hit upon this relatively lightly. If we were a proof-oriented class, the mean value theorem is a very significant theorem that allows us to prove a lot of the tools that we'll be using later on. But as this is Calculus 1 and we're mostly interested in using the tools as opposed to proving the tools, going into mean value theorem more deeply isn't appropriate here, but you can trust me that in the great world of mathematics, it's a significant theorem. Now, before we can get to the mean value theorem, we have Rolle's theorem, which says suppose y equals f of x is continuous at every point in a closed interval ab and differentiable at every point in an open interval ab. If f of a equals f of b, then there's at least one number c in the open interval ab such that f prime of c equals 0. Now, one thing that maybe we can begin to start understanding about theorems and mathematics kind of in general is that when we're talking about theorems, theorems have hypotheses and conclusions. When you're given a theorem, what it's basically saying is if these things are true, if the hypotheses are true, then you are guaranteed whatever that conclusion is. In Rolle's theorem, the hypotheses are here. Suppose y equals f of x is continuous at every point in a closed interval a to b, differentiable at every point in an open interval ab, and f of a equals f of b. So Rolle's theorem has three hypotheses: continuity on the closed interval, differentiability on the open interval, and then equality at the endpoints, f of a equals f of b. The conclusion then is that there is at least one number c in the open interval ab such that f prime of c equals 0. So down here we have kind of a graphical representation of what Rolle's theorem. So the picture shown below satisfies the hypotheses of Rolle's theorem. It is continuous on the closed interval AB. Remember what continuous means: no gaps, breaks, or holes. So it's continuous on IAB, and that's what it says there: no gaps, breaks, or holes. Differentiable on AB. And remember, differentiable meant graphically that there were no discontinuities, corner points, cusps, or vertical tangents. So we have the differentiability on AB, and f of a equals f of b, that the y coordinates are the same. That's what, when we say f of a equals f of b, remember y coordinates come from plugging into the function. So my y coordinate here would be f of a, my y coordinate over here would be f of b. And when we say f of a equals f of b, that means those y coordinates are the same. So that's why I can draw a horizontal line through those two guys, because the y coordinates are the same value. Then the conclusion says that there's at least one number c, and it says at least one, there could be more than one, at least one number c in the open interval ab such that f prime of c equals 0 must be true. In the graph above, how many numbers c satisfy the conclusions? Where are the numbers on the x-axis? Again, I'm lecturing to an empty classroom, so no one's here to answer it. But if people were, kind of looking confused and whatnot, I'd say, remember what the derivative at a point tells you. Derivative at a point tells you slope. So when we see f prime of c equals 0, means trying to write things sort of legible. The slope at c is 0. And then we talked about before what that means graphically. So there is a horizontal tangent at 0. Well, there are two places that do that. Right here, there would be a horizontal tangent. Or actually, at 3 places. Didn't look at my graph right there. Right there, there'd be a horizontal tangent. And right there, there'd be a horizontal tangent. So I could call that C1, C2, C3. So the answer to the question below, are there 3 numbers C that satisfy the conclusion of Rolle's theorem? And there you see them placed on the x-axis. That Rolle's theorem says that there's at least one number C between A and B where we have horizontal tangents. In this case, we have 3 of them. So there's what Rolle's theorem says. And like I said, if we were a proof-oriented class, we need Rolle's theorem in order to go and prove the mean value theorem, at least prove the mean value theorem more easily. So now the mean value theorem. Suppose y equal f of x is continuous on a closed interval ab and differentiable on the open interval ab. Then there's at least one number c in the open interval ab such that f prime of c equals f of b minus f of a, all divided by the quantity b minus a. Okay, so my hypotheses here are just 2. My hypotheses, right here, the hypothesis of the mean value theorem are y equals f of x is continuous on the closed interval and differentiable on the open interval. Just 2 hypotheses. Rolle's theorem had 3 hypotheses. The continuity on the closed interval, differentiability on the open interval, and then f of a equals f of b. That was Rolle's theorem. Mean value theorem, you get rid of the f of a equals f of b. Mean value theorem is more general. It doesn't have that specific thing, f of a equals f of b. Then the conclusion to the mean value theorem is that there's at least one number c in AB such that f prime of c equals f of b minus f of a. So trying to understand what this thing says graphically. So the picture shown below satisfies the hypotheses of the mean value theorem. Continuity on the closed interval. Now I drew this a little bit further than I needed to. So we're only really talking about the curve right here on the interval in question, a to b. But we have continuity from A to B, no gaps, breaks, or holes, and differentiability, no discontinuities, no corner points, cusps, vertical tangents. So we have the hypotheses. So that means that number C must be true. But what on earth does that, we got this really funky formula there. F prime of C equals f of b minus f of a over b minus a. How on earth can I visualize that? So let's try to visualize it. And I am going to draw a secant line here. So I'm going to draw, we'll draw it in blue, why not? I'm going to draw the secant line here. Remember, a secant line goes through a curve in a certain neighborhood in 2 points. I have no idea what the curve might be doing up over there. I have no idea what the curve could be doing over here. But in the neighborhood that we're looking at, that secant line goes through those 2 points. And so that's my secant line. And easy enough, we'll go down below and do this. Without too much fuss, I can find the slope of that secant line just using the standard formula for slope. And so that's going to be f of b minus f of a over b minus a. Just using my points there. x1, y1, x2, y2. So there's the slope of my secant line. So that's the second half of the conclusion here. Now if I look at it, remember f prime of c equals the slope of a tangent line of the tangent at x equals c. That's one of the main interpretations of slope, that it gives you slope of the tangent line. And so what this is saying, f prime of c equals f of b minus f of a over b minus a, says slope of tangent equals slope of secant lines. So we already said that that guy was the slope of the secant, f of b minus f of a over b minus a. Well, if the slopes are equal, and again I would ask the class this, if the slopes are equal, what's that tell me about those lines? So tangent and secant lines must be parallel. So I go back up and look at my whole picture, then I can get it all in there. Notice if I draw a line right there. and call that my tangent line, I do find a place where they're equal. And so that C that they're talking about in this picture is right there. So what the mean value theorem is saying graphically is when you have these hypotheses, continuous on the closed interval AB, differentiable on the open interval AB, then there will always be at least one number between A and B where the tangent line, or one point between A and B, where the tangent line and the secant lines are parallel. That you will always be able to find this number C, that when I draw the tangent line will be parallel to the secant line. That you can always, always find that value C where the tangent and the secant line are parallel. So that's what it's saying visually. Now we're going to practice a couple problems just finding that value C. And again, we're not going into great details. We're not going to use the mean value theorem to prove substantial results in mathematics, although you can. At this point, we're just going to practice using the theorem on some basic cases. And that's what we'll see on the next video.